Hi, hi everyone. Good afternoon, and I'm Kalapriya, and I'm going to be the session chair for this tutorial. This is an interesting topic. It's going to look at different angle more from the infrastructure aspects of using and making the big data and machine learning go green. So we have Rishabh from TCS Research, Karthik from Jadavpur University, and Sunirmal from University of Calcutta, who would give us this tutorial or walk through the tutorial. And before I hand it over to them, welcome you all once again to this tutorial and happy learning in this session. So over to you, Karthik, or one of you from your speakers.
Yeah. So good afternoon, everybody. So in this tutorial number 8, green computing for big data and machine learning, I will start the presentation. Myself, Karthik Chandra Mondal from Jadavpur University, followed by Rishabh Bokul Bodo from TCS Research, will present his part, and the last part will be presented by Sunimal Khatwa from Calcutta University. So, with this short introduction, going to the next slide, that is green computing for big data and machine learning. Now, to make it any computing platform to make it green, there are several aspects to make it right. So, some aspect belongs to software part, some aspect belongs to hardware part, and we will not cover all the approaches or all the strategies from hardware and software, but we will focus on a specific topic from software and another specific topic from hardware. So if you look at the software part, then we will
So,
mainly
Karthik, can I just interrupt a minute? I
yes,
just want to ask the participants if you have any Q&A, can you just post it on the Q&A chat that you will see? It will be specifically written as Q&A so that I can take it up to the speakers. Thanks, Karthik.
yeah. So thank you, ma'am. So if you have any query, you can please write your query, or you can ask it if it is possible. I don't know. So anyway, so for approximate computing from the software part, there are several approaches or several strategies are available, and among those strategies, we will focus mainly on the approximate computing, approximating in different aspect of the software topic or software components, like from algorithm, from storage perspective, from processes, or from code. And by this different in this different portion of this approximating the processes, we will try to make a balance between the quality of the result and the performance of the approach. And by this way, we will try to make the computing resources or computing processes green. Another part, which is the harder part, where we will mainly focus on the power modeling, that will be mainly presented by the last speaker, Dr. Sunimal Khatwa. And this first part, that is approximate computing, which will be presented, the introduction and the few steps or few approaches will be explained by me, and the rest will be explained by Rishabh. So with this, now the question is, which motivates us for this green computing research, or why we are here to present this topic for green computing. The question is, or the answer, you can say that whenever you look for any data analytics or any kind of computing techniques, uh, all these computing techniques takes a lot of power or consume a lot of power during the processing, right? And when you consume power, that power comes with some carbon emission, and carbon footprints actually tells you that amount of carbon emission along with other greenhouse gases during that uh, during that computing processes. When it processes, that it consumes power, and that power consumption actually generates carbon footprint. So, just for example, if we look at the Google search engine alone, and this Google search engine for a particular user, it generates 0.01 kg of carbon dioxide. It is an estimated in the 2015, and Google search engine processes 3.5 billion of requests every day approximately. So you can imagine how much greenhouse gases actually emitted by Google search engine alone. Now, if you consider a scenario where a particular user who actually does 25 searches per day and watch 60 minutes of YouTube videos along with usual Google or along with usual Google services like Gmail and other, that particular user emits the greenhouse gases, which is in 1 month is equivalent to driving a car in 1 mile only. So you can just imagine that how much greenhouse gases are generated by all the Google user in a year. So considering the another fact, which is by Facebook in the year 2016 or 2016, it says or it demands that 30 grams of carbon dioxide is emitted by per user per year, and which is the study of 2016 or 2015-16. And in 2020 they says that they reduce this greenhouse gas emission by 80%. Okay, so and they in the recent report by Facebook, they are saying that they are producing 12 gram of carbon dioxide by every user, by using this company's services every year, and their target is to reach a net zero state. What is this net zero state? Net zero state is a state where the greenhouse gases or carbon footprint emitted in the atmosphere is equivalent to the greenhouse gases uh, consumed by this atmosphere. That means that there is a balanced state. There will be no that that what I can say, that global warming in the earth. And Facebook has a target to reach in that balanced state, that net zero state by 2030. But the thing is how? Question is how we can reach in this state, right? So that is a particular case of Facebook and Google. Now, if you consider the global or whole ICT sector or ICT industry, then as per a report in 2015, it says that 3.6% of global electricity is actually used by ICT industry only. Okay, and by using this global electricity, they generates 1.4% of global carbon emission. And among this 1.4% of global carbon emission, if you look at the percentage of global carbon emission by different components of this ICT industry, like PC and monitor generates 39% of this portion, whichever is generated by this ICT industry, and server including its cooling instrument, it generates 23% of this total carbon emission, and the rest, that means more than 60%, is actually by only this PC and server, and the rest are by different telecom components and printers and all. Okay, so if you look at this data, then it is very much clear that this carbon emission is actually done by these processing units like server or data centers or the PCs. Mainly these components are actually generating the global carbon emissions among these IT sectors, ICT industries. So this raise the performance demands will soon outpace the growth in resource budget, and this over provisioning the resources alone will not help the problem of the computing industry in near future. And that's the portion, or that's the place where researchers are interested to work on this particular topic of green computing, to find out the a computing system which is energy efficient, or you can say a computing system which is green or near green. Okay, so now the thing is how we can reduce this carbon footprint in an acceptable range, so that the computing resources can be called as a green. And there are many solutions are available, and as I said, we will mainly focus on the approximate computing and power model, and there are many other like inexact analytics or resource scheduling, etc., and so etc. are there. If you find our presentation is interesting, and you can then later on you can work on this, we will give you some uh, bibliographies, resources there. From there you can get more on these topics. Now the thing is, approximate. What is this approximate computing? Approximate computing is nothing but a paradigm where we try to balance the energy consumed and the time taken by a particular process with the accuracy of the output. Okay, so there is a trade-off between energy computing time, energy consumption, computing time, and the accuracy of the output, right? So this approximate computing does not generate accurate result because there is a trade-off between the accuracy of the output. So that means it does not generate accurate result. It gives approximate result, and that's the name comes the approximate computing. Okay, so from exact computing we come to approximate computing, where computing resources generates approximate result. And this approximate computing actually reduces the number of reduces the number of energy consumption by reducing the number of operations present in that particular operation, in that particular computing, and which in turn also reducing the computing time. Right. So many computing intensive process and tasks may not require accuracy. Like for example, there are many applications available, from machine learning to neural NLP to database search or big data analytics. There are many applications are available where a good enough result is acceptable or solve the purpose for that particular application. Okay, so on that particular domain, you can only apply approximate computing. Not everywhere on those domain you can apply approximate computing. Now, for example, if you look at k-mean clustering, right? K-mean clustering is a well-known clustering algorithm in the data mining or machine learning. If you get 5% accuracy loss in the result set of k-mean, that is not that much problematic for a particular domain. 5% accuracy loss by the k-mean clustering results, and by this 5% accuracy loss in the k-mean clustering result, you can save 50 times of energy compared to the exact result by this k-mean clustering on the same application on the same data. Right, so you can just imagine how much energy you can save with a little bit of accuracy loss in the result set. Similarly, in case of accelerated inverse kinematic application, by using natural neural network approximation, if you lose 5% in the quality of result, you can achieve 26 times of energy savings compared to the exact result. Okay, so these are just two sample examples where you can see the effect of approximate computing compared to the, or you can see the trade-off between the approximate computing result set along with the energy saving by that particular process. Right. So approximate computing exploits the gap between the accuracy required by the application and
I think there is an issue with the network.
Yes, ma'am.
Okay,
I
we'll
think,
give it a minute, and if it
yeah,
doesn't, then probably one of you can project
yeah,
it.
yeah, sure.
All right. Okay. Should one of you be able to project, and then when Karthik joins, he can take it up?
Let me try to share the screen.
Sure.
Oh, one actually I am not able to share because I think he's still in the share mode. I think so. My share button is not active.
Okay. Okay, just a minute. I'll just try taking some help from the host.
Is it now? I for the time being I hid him from the stage. Can you share now?
So Rishabh,
Yes.
are you able to see the button now? I think Atul has enabled it.
Risha, can you hear us? You are
Hello. Yeah,
muted. So
it
if you are,
is.
yeah.
Yeah, actually,
Let,
it is still inactive.
really?
Yeah.
Okay, let me try to hide you and then bring back. Okay, try now.
No, still inactive.
That is pretty strange. Can somebody else share on your behalf?
Yeah, maybe Sunirmal or somebody can share it and maybe you can walk through it or one of you can walk through
The
it.
same thing has happened to me also. So I think we have to instruct Kartik Mandal to stop sharing through message.
Yeah, if you could do that, because if you have his number or something, you could
Yes, yes.
try quickly talking to him.
Is Karthik back? I put him back in the stage.
Yeah, Atul, for me also it says only one person can share the
Yeah,
screen.
it has
Otherwise, I can get the
some
slides and share
the
it from my side.
stage. So let me try pausing the session and then start again.
Sure.
Yes, I think
Actually,
it was
now I
enabled.
can see
It
the
is
thing.
enabled now.
Yes.
Yeah,
Yeah.
we can
Yeah.
start.
Yeah, I think it is enabled. Yes. Thank
Sure.
you.
Yeah.
Sorry about
Hey, welcome
the
back, Karthik.
disturbance. Yeah, where I left, I don't know where when this stopped.
Okay. So you can share or should I share?
I will say I let me complete because I have few minutes to finish my portion. So let me try. It is audible, right?
Yeah, yeah.
So, Karthik, I think you can start
Okay.
sharing and probably go over a couple of slides in brief. That's all right. I mean, in the sense, go back one or two slides and you could summarize that. That would be okay.
Okay. So can you see my screen? Is it
Yeah,
visible?
it's visible.
Okay.
Yes.
So this portion,
Yeah, maybe you can start with
do's and don'ts.
yeah, perhaps.
Okay. So, if I talk about the do's and don'ts of approximate computing, so you can say that you can see that the noisy data, in case of noisy data or floating point operations, it is advisable to use this approximate computing. But in case of non-critical data, where the little bit of approximation in the results will not harm much in that particular application, you can use approximate computing. So now the question is how you can apply this approximate computing in a approximate computing in uh, in a particular problem, in a particular solution. It is basically three-stage process. First step is identifying the proportion where you can apply this approximate computing, and then there the first module is the identification of the code segment where you can apply approximation. And there is a tool called Valgrind Profiler which gives you two values for a particular function available for a particular solution. And one value is called resource usage percentage, and the second value is called number of times they have been called. Okay. So if you multiply these two value, the value you will get is the greater the value, greater is the resource consumption. So you have to shortlist all based on these two, based on the multiplication of these two value, and then you take 20% or 50% or 30% of the topmost functions where you can apply this approximation in the process. Now, after deciding the places where you can apply approximation, next thing is you have to implement that approximation by using different strategies, which we will see very soon. And then after implementing those strategy, we will check for the qualities of the result by using different matrices, and then we will try to find out the trade-off between the quality and the output or the error generated by that particular implementation. And at certain point where the error is low but energy is also consumed, also like saved a lot, then we can at that particular situation we can implementation. If you talk about quality application, what is then quality
So, Karthik,
there are
there seems to be
PASNR like
some
P and in case
voice.
of processing and division, they result noise in case of image processing and computer view.
Hi, Karthik. There seems to be some
Hello,
voice
hello.
issue. So, if you could just check and
Voice from my side.
yes, yeah, you can continue. We'll see how it goes.
Okay.
Actually, the voice is breaking bit.
So little okay. Just okay. Another so another matrix that is another case is and machine learning. We are studying like for estimate error, uh, for result solution.
So, Rishabh, is that possible that one of you can present it, please?
Rishabh,
Hello.
yeah,
We can hear
can
you,
you
Rishabh.
please
Yeah,
go ahead
actually,
with this?
yeah. Actually, your voice is breaking. Let me take it over.
Yeah, from that the quality matrix.
Yeah, you can please unshare your screen so that I can share. Otherwise, I will not be able to share.
Yeah, I will answer, right?
Yeah, you can unshare. Then I can actually share.
Yeah, it is shared already.
Yeah, yeah.
So you can present it, I think.
Is my screen visible?
Yes.
Okay, and my voice is fine.
Yeah, that's right. Yeah, clear.
Okay, so Kartik was talking about the basics of approximate computing and green computing, and how we can implement approximate computing in various domains and some steps. So I think he talked till this slide. So here is the trade-off between quality and the energy savings, and also speed up between various versions of an algorithm or a program. So by injecting some amount of error in the program, we can save energy, because if we inject some amount of error, or if we do some amount of approximation in the code, then the number of machine cycles to execute the program will be reduced. And if the number of machine cycles are reduced, then the amount of energy required to run the code or execute the code will be reduced. And the speed of the execution of the program will also increase. So we have to find a trade-off between the error, the amount of error that is induced, and the amount of energy and the speed that we have achieved in any program. And we have to select the most optimum out of those versions of approximate code for our application. So here are some applications and some matrices which we can consider while dealing with various different programs which falls in those particular domain. So the basic idea is that we have to compare between two versions of the same program. The first version is the exact execution of the program, and the second version is the approximate execution of the program. And the output that we get out of both the execution, we have to compare using some quality metrics. Now this quality metrics can be different for different applications. For example, for image processing, or we can say age detection kind of application, we can have the pixel difference between the output of the exact and the approximate version of the code. And then for data mining, we can have the in case of data mining, we have various tasks like clustering, classification, and all those kinds of different grouping algorithms are there. So we can have the accuracy of clustering and classification. We can compare the accuracy of clustering and classification for the exact and the approximate version, and check how much error is induced in the scale of 0 to 1. Okay, in the scale of 0 to 1, if the result is 0, then both the exact and the approximate version of the code gives the same result. And if it is 1, then the result is 100% different than the exact result. So there is a huge amount of error induced in the program. So we have to avoid getting errors that ranges from zero point 0.5 to 1. We should keep the error lower than 0.5 in the scale of 0 to 1. So all these things will be shown in details in the next slides. So here you can see some techniques that we can use in approximate computing, and we have experimented and worked with some of them, if not all. Okay, so memory access skipping, memorization, precision scaling, task dropping, then loop perforation. So all these methods are been implemented by various researchers across the world. And many researchers have also come up with different compilers which are actually approximate inherently. Okay, so we have C++ compilers which are created on top of some LLVM reusable compiler toolchain, which can actually approximate your program, approximate your algorithm inherently. You just need to give the exact version of the program, and it will give you the approximate version along with the results and the error induced in the particular version of the program. So we did a survey in 2019 to check the current state of the art in approximate computing, and we found that the number of papers that we cited, among them 50% of the papers dealt with approximate computing in the code level and algorithm level, and 6% was dealing with approximate communication. So another subtopic of approximate computing is approximate communication, where the communication between two machines or the networks that we use in today's world. So those are approximated, and the data that is being transferred from one node to another is somewhat approximated without incurring much error that is not acceptable for the user. Okay, so that is one thing. Then in the hardware or the circuit level, there is 31% work has been done out of the survey, and finally 13% in the cloud computing scenario. So as I listed some of the approximate strategies, so memory access skipping is one of the most important one out of it. So here what we do is that when the processor is trying to access some data from main memory or the caches, they do not access the entire set of data, but a particular subpart of the entire data, and this has to be monitored in such a way that the application for which this memory access skipping is been actually implemented do not get harm, or it is not harm at the overall execution of the program. So there are some problems in computer vision, for example, where pixels we have to process each pixel in an image for edge detection or object detection or any such kind of activities. So there, if you skip some of the pixels in between while processing each and every pixel of an image, then it will not harm much into the output of the final detection problem or any other computer vision problem. So, but the thing is that skipping some of the pixels from the entire set of pixels while processing will not incur much error, but it will save a lot of energy, and it will speed up the execution of the program twofold to tenfold. Okay, so this is what is the memory access skipping deals with. Then memorization is another technique where actually you store the results of previous execution of a program and utilize it directly in a new execution of a program or another subtask of a huge task. So you store results that can be reusable, or which are supposed to be reused in different parts of the same larger program. Then loop perforation is another important technique where you find some of the resource hungry loops in a program and skip some of the loops in between using various methods. Maybe you skip alternate loops, or maybe you skip some loops at the starting of the entire loop execution, or some loops at the end of the loop execution. But this has to be done in a very in such a way that you actually know the behavior of the program entirely. You know the behavior of skipping loops in that particular program. You have to do it in a very careful way. So there are various methods which are being utilized in approximate computing, which can actually guarantee you the or which can serve as a reliability factor in approximating programs and keeping the error under a particular threshold. For example, in a particular application, suppose the maximum limit for error that is tolerable is 5%. Then you can you can execute the approximate computing technique in such a way that the overall error that is incurred for any approximate version of the program will not actually cross this 5% error limit. Then precision scaling is another important method where you scale the precision of floating point numbers. Okay, so in most of the programs in big data analytics and machine learning, we do not deal with fixed numbers. We deal with floating point numbers. So the data is often represented in floating point numbers. So there, if you reduce the accuracy of representation of these floating point numbers, then definitely there is a cut in the amount of time required to store and retrieve the data. Okay, so those kind of methods are also been used in approximate computing to reduce execution time and save energy. So in case of algorithms, the approach that we use to actually do approximation using some of the methods that I have already described in the previous slides. So what we do is that we try to implement any approximate technique, for example, like loop perforation or precision scaling or memorization. Then after performing this approximation, we try to check the result of the execution of the program, and we try to compare the result with the exact result. If it is tolerable, then we accept it. If not, then we change the approximate strategy and the portions of the code where we are approximating, and we again check it. So we do it in an iterative manner until and unless we find a perfect approximate strategy for the particular program that we are executing, be it a machine learning program or a big data analytic program. And finally, we freeze the strategy when we find an optimal result or an optimal trade-off between the error and the energy savings and the speed up. So here is an example of how we can actually approximate a program. So in case of any program, there are various execution paths that exist. So here site is nothing but a part of a program. So site 1 to site n+4 are various sites in a program, and the arrows show the execution path of a particular program. So here these arrows mean that from site 1 it can go to site 2, 3 or n. Then from all these sites it can go to site n+1. There is only one option, and from n+1 there are two options, n+2, n+3, and finally to n+4. So if we induce approximation in site 2 and the execution follows the path like site 1 to 2 to n+1 to n+2 to n+4, then this the error induced for this approximation, that is delta E0, will be incurred. So finally, if we induce error or approximation inside n+1, that is delta E1, then the path will, since delta E1 is there in site n+1, and n+1 is common for all the execution paths, so it will be a common approximation portion, or the error that has been induced here will be common for all the execution paths. So finally, let us consider the last execution path, that is site 1 to 2 to n+1 to n+2 to n+4. So this is a path where all the three approximation sites are present: site 2, site n+1, and site n+2. That is delta E0, delta E1, and delta E2. So this path is the only path which has all the three errors of approximation. So all the three errors will be added to form the final error for this particular path. So we have to actually check which are the portions where we have to do the approximation, so that the overall execution of the program do not exceed a particular error threshold. So that way we have to find the various code segments and various areas in a particular program where we can do approximation. So one technique for approximate computing is load value approximation. So generally, when the processor tries to process a program, it tries to take data from some caches, and if it is missed, then it goes to the main memory. Okay, so this actually incurs some amount of time. Okay, so it requires some amount of time to move from the cache to the main memory and then back from the memory to cache to the processor. Now, if instead of this miss in the cache, we can approximate the value that the processor wants and without going to the main memory, then it will save some time. So this is what load value approximation does. Okay, it actually tries to approximate the value that is present in the main memory and that is been missed by the processor in the cache. And finally, it takes that value from the cache without going to the main memory after a miss. So indirectly, we can say that there is no miss actually. Although there is a miss, but there is no miss because the value that the processor requires is being approximated using this load value approximation in the cache. So another technique of approximate computing can be we can divide a algorithm, the program of an algorithm, the code of an algorithm into some parts, and these parts consist of the actual control instructions and the data movement instructions. Okay, and we can keep the control instructions as it is without doing approximation, because if we do approximation in the control instructions of a program, then there can be some serious consequences like crashing of the program itself. So we consider the data movement part of the program and we do some approximation like load value approximation or like precision scaling or like missing some memory accesses. All those kind of techniques that I have already stated in the previous slides can be incorporated and we can achieve approximation. Then another technique is the DRAM refresh reduction. So what we can do is that each and every program that we work on, be it concerned with big data or machine learning, we have some critical parts and we have some non-critical parts of the program. So now, while running it, the operating system often try to do paging of the program. So if we can divide the pages into critical and non-critical pages, then in the DRAM, we can actually do refreshing of the critical pages normally, and we can do the refreshing of the non-critical pages in a more economical way. So since these are non-critical pages, then that implies that not refreshing them often will not harm the execution of the program much. But if you do the same thing for the critical pages, then there can be serious consequences. So we can actually distribute the pages into two parts. The first part is the normal refresh rate, and the second part is the low refresh rate. And this method by which we do this is called the approximate DRAM. So this is one important method of doing approximation in the operating system level. Another important technique of doing approximation is on the basis of spatial locality. So we all know what is spatial locality. So we often store the similar kind of data nearby to the nearby each other in locations, in memory locations. So if we actually store similar kind of data or similar data near in the nearby locations in memory, then the program should be able to actually know that if a particular data is required to be fetched or to be stored, then it knows where it should actually search without searching the entire location, without searching the entire chunk of storage. So in those cases, you have to actually we can incorporate this value similarity based spatial locality, which will actually reduce the search time of the program for finding any data or for storing the data in any location. Then we have the inexact writes in the NVM, that is the virtual memory. Okay, so normally the data which we store in any particular location that is normally been executed by a particular program, and it tends to change each time we run a program or each time we run a subpart of a program. So normally big data related programs are huge and they have many subparts or subtasks. Let's consider the MapReduce paradigm that we often use in the tools like Hadoop and Spark and all those that we have in today's world, also implemented in the cloud infrastructure as well. So those programs have many subparts or subprograms in the entirety. So if we can find those programs, subprograms, which actually gives us similar results, or the data that has been generated by the subprogram are similar to some other subprograms or previously run program, then we can actually store those program permanently in some memory locations without changing those data or without overwriting those data, and we can directly access those data whenever required. So we can save some write operations by doing so. So whenever there are similar kind of data that is to be written to the memory locations, then it actually bypasses those kind of operations, saving some amount of time, and in turn saving memory access energy requirement and time. Now coming to the neural network based approximation. So when we talk about machine learning, all of we talk about the neural network, because most of the applications in today's world, be it image processing or natural language processing, most of the applications use neural network, various forms of neural networks such as RNN, CNN, graph neural networks are there nowadays. So various kinds of neural networks we have, and we all know that neural networks are not exact in nature. Those networks are already approximated. So neural network is nothing but an approximate network. Okay, so if in an exact program, there are some portions which are approximable, so we have to find those portions which are approximable, and we actually replace those portions with a small neural network maybe, then we can save a lot of energy and time requirement for execution of that particular program. So this is one method that is widely used uh, in various areas. So those programs where neural networks are inherently used in machine learning, so those already are approximated. But some of the programs which do not inherently use neural networks as their background, so we can find portions, at least some portions of the program, where we can replace the program portions with smaller neural networks to mimic an approximate behavior of the exact program and save some energy and time. So similarly, in the neural network itself, we can do some approximation by replacing the various neural units or neurons with some approximate neurons. Okay, so I will not go into the depths of this method, but you can have a look into our tutorial paper. Those papers that we have cited in our paper, those papers talk about various methods where we can approximate the neurons of a neural network itself. Okay, so that is one important method by which you can actually approximate the already approximated neural network further, and in turn saving some energy in the learning as well as prediction task. So one of the most important part in machine learning is the learning part. So learning takes a lot of time if the amount of data is huge. If we are learning on a very huge data set, then it will take days to complete if we do not have proper infrastructure. So to speed up the learning process and also the prediction task after the learning process, we can approximate the neurons of the neural network, and we have some methods to do that. But that is out of the scope of today's tutorial. You can have a look at our tutorial paper for details. Now I am going to speak about some of the use cases where we used different approximate computing methods, and we achieved some amount of advantage out of it. So here in the screen you can see a robotic path planning algorithm that we have approximated. So the first case in the top left corner, the yellow line is the path been planned by a robot from the original 00 location. Okay, and this yellow path is, and these red triangles are nothing but some obstacles in the scene or the environment where the robot is working. So the first image, in the top image, the robot is moving from this point to the end point in a straightforward manner by planning the path, considering all the obstacles in the environment. The same thing, if we approximate using approximate computing techniques like loop perforation and precision scaling, it actually plans a different path. You can see the second path in pink. The same algorithm is planning a different path for the same starting and ending point of a robot, but the execution time is much lower in the second part, second planning than the first planning. Here also we have to consider the actuation part, because if there are more turns and twists and turns in the path, then the amount of energy requirement will be higher. And if the path is straightforward, then the energy requirements will be lower. So there should be a trade-off between all these factors to actually consider which approximation strategy will give us the most optimal energy savings and the minimum error which is tolerable. Okay, so that is what is we want to convey here. So the path in the second case is a bit longer because there is a turn in between. Okay, that is not there in the first path. So there are some extra energy requirement in this turn in the actuation part of the robot. So those things needs to be taken care of while we do approximation. Then second case is in the k-nearest neighbor algorithm, we actually implemented loop perforation in the particular loop that has been highlighted. So the left-hand side is the exact execution, and the right-hand side is the approximate execution of the same KNN algorithm. Okay, so we have approximated the loop that has been highlighted, the for loop, and in result we can see that, so we have actually tried it in a small amount of data, so the execution time difference is not that much high. In the left hand side it took 0.38 second to execute, in the right hand side it took 0.28 second to execute, and the result of clustering of this KNN algorithm is almost similar, you can see in both the cases. So the clustering result is shown in the images in red and green clusters. So for a small amount of data, the difference is from 0.38 to 0.28. But just imagine if you are working with a huge amount of data in the same algorithm, then you can imagine how much difference in the time, execution time will be there with a minimum error in the clustering results. Similarly, we applied the approximate computing method in finding rules, so association rule mining. So in the first case, the exact execution of the rule mining algorithm gave us three different T1, T2, and T3 transactions with different items, I1 to I6, and I1, I2, I4, I6 in the first transaction, in the second I2, I3, I4, in the third transaction I1, I2, I4, I6, I10. Similarly, the approximate execution of the same algorithm gave us two different transactions. The third transaction was missing. So for a small amount of data, we can see that we missed one transaction in the rule mining algorithm. And for a huge amount of data, I have not shown the results here, we actually missed some of the transactions, but that was not that much hazardous for the output that the user wanted. So that amount of error in finding rules or doing association rule mining for exact system and approximate system, the comparison is somewhat tolerable, and the amount of energy saved was huge, and the time savings, the amount of time that required for the execution of the exact system and the approximate system, the comparison was actually much huge. So approximate system was executed in as far as I remember 4x times faster than the exact system, with 5 to 10% error in finding the rules, the association rules. Okay, so here you can see the results. The same the rule mining algorithm that we approximated. You can see for small amount of data, the time requirement for exact and approximate computing is lesser. But when you grow the amount of data on which the algorithm is being run, for example, say 1 lakh or 5 lakh of data, then you can see the difference in execution time. So for the last case, in the left-hand side graph, you can see the first, the exact execution takes 54 seconds, and the approximate execution just takes 20 seconds. That is less than half than the exact execution of the program for a priori algorithm. Okay. So one more use case we actually ran on a SLAM algorithm. SLAM is a computer vision algorithm that finds the map, that creates the map of an environment and localize a particular agent or a robot in the particular map. Creation of map and localization of a particular agent like a robot in the map, his current position with respect to the entire map. So there we did approximation using some resource-hungry functions. We found some resource-hungry functions using the Valgrind profiler, the profiler that already Dr. Kartik has talked about in the previous slides. So we approximated, and we found that the results, the left hand side and the right hand side, are the exact and the approximate results. Those are almost similar to each other. You can see the maps are almost similar. Just the left hand side map is bit in an angular fashion, but almost similar. So these were some of the results, and these were some of the functions that we approximated. Greedy search inside that particular algorithm, hierarchical search, and all those functions were approximated. And as we used the loop perforation method here, so as we increased the loop perforation rate, the computational speed up also increased. Okay, so you can see in the first graph. In the second graph, as we increased the loop perforation, the computational speed up increased, and also the error was increased, but it was under 10% for all the cases. So that was tolerable in that case. So now coming to one important compiler that has been created on top of LLVM compiler toolchain. Okay, so this compiler is an approximate compiler that was created in University of Washington, and it can be used directly to actually approximate any kind of machine learning or big data related code. Okay, you just need to feed the compiler with a exact version of the code, and it will give you the approximate version of the code, provided you give some annotations. So I will show you. So this is the overall execution of the toolchain. So you give a program, exact version of a program with some annotations, and you give the quality metrics to compare between the exact and approximate version. Then it does some analysis. It puts some approximations in various parts of the code. Then it does some tuning, and it gives you the candidate codes. Okay, and also along with the codes, it gives you the result of all the approximate execution of the code. So from them you can select which approximate version that you require for your particular program, and with how much error percentage that you require. Maybe 5% or 10% is the maximum limit for your particular application. So this way it actually does. In the lower part of the slide, you can see that it gives us result as which loops can be approximated, which loops cannot be approximated. So the compiler gives you this result if you fit a exact version of a program into the compiler. Okay, so here you can see that the loop that is in the 651 line, that can be approximated or can be perforated. Then another loop that is in another line that is there in the program that cannot be approximated, because if you approximate that loop, then there will be a huge amount of error. But if you approximate the first loop, there will be lesser amount of error that is tolerable. So that way you can find different versions of the program which are approximated in different areas, and you can choose from these various versions which version you require for your particular application. So basically this compiler, accept compiler toolchain, uses three different approximation methods. Okay, so the loop perforation is used, and then precision scaling is used, and your load value approximation is used. These three methods are used in this compiler toolchain. Now, how will you actually fit the program into the particular toolchain? So here you can see that there are two keywords, approx and endorse, given. So whenever you fit your program, the exact version of your program, into this compiler toolchain, you have to put the keyword approx in front of any loop or in front of any variable that you want to approximate. Okay, And whenever you want to actually use the exact version of the loop or the variable, then you have to put the keyword endorse in front of it. For example, here you can see approx int a equal to something, some function. So this means that we are telling the compiler to approximate this particular variable a. And in the second case, we are telling the compiler to use the exact version or the precise version of this variable a, endorse. Okay, so this way you have to actually annotate your program to identify various approximate regions in the program and find out the most optimum approximation strategy and combination of various sub areas of the program to run. So here is an example of a quality metric that you have to feed into the compiler along with your program. So there are two functions, the load and the score function. Okay, the load function actually loads the output of the program two times. First the exact execution, second the approximate execution. And then the score function actually does the comparison between the original output and the relaxed output. Okay, so these two functions are used in that particular compiler, accept compiler, which compares between the exact output and the approximate output and gives a value from 0 to 1. So here we are just doing a simple calculation between the output of the exact version and the approximate version. So this program load and score will change on the basis of the program you are running. If you are running a image processing program, then maybe here you have to find the difference between the pixel, each pixel from the exact output and the approximate output. If you are doing this for a data mining algorithm, then you have to actually find the accuracy. We have to find the difference between the accuracy for each of the cluster formations for the exact and the approximate output. So this heavily depends on the application and the code that you are running. Okay, so if the value is 0, that means there is no difference in the output between the exact and the approximate version. And if the value is 1, if it returns a 1 value, that means there is 100% difference between the exact and the approximate output. That way you will be able to do a quality control on your approximate computing method when you are running exact version and the approximate version of a particular program, and check whether you are getting any energy and speed benefit or not. So these are the results that were achieved by running various applications in the accept approximate compiler. So there are various different applications. You can see Keniel, FluidMate, Stream Cluster, Sobel. Sobel is a image processing method. So all these were being tested. These programs were being tested in this approximate compiler, and various speed up for various applications were achieved. You can see some were scaled to 5x as well. 5x speed up was achieved in some of the applications. So these were some comparisons done on various applications of that particular compiler. So the details of this compiler, how to use this compiler, how to run this compiler can be found in their website. You can go through the paper of accept compiler. There the links for the GitLab pages are there, GitHub pages are there, and you can directly download this compiler toolchain in your machine, and you can start working on this compiler. You can build on this compiler. You can use this compiler for bringing energy efficiency in various machine learning and data mining tasks directly. So it is free. It has a license, but it is free. Anyone can use it for research purpose. Now coming to the last part of the of my part. So there is a approximate version of the Hadoop framework itself. Okay, so you can find the program of approximate Hadoop in GitHub. So what it does is that it does a combination of task keeping and sampling. So in normal Hadoop, the MapReduce paradigm is used, where we use a key value pair, and execution is done in a distributed and a parallel manner for various blocks of code and various parts of the same data. The data is distributed among various blocks, and then it is fetched, and then it is executed in a select and reduce kind of a fashion. So MapReduce functionality is been used. But the difference in approx Hadoop is that you do not select all the blocks from the program, but only a few blocks. So for example, here you can see block 1, block 3, and block 5 are selected to go forward. Block 2 and block 4 are omitted. So you are dropping block 2 and 4. So that is what is called as task dropping. You are dropping 2 tasks and considering only 3 tasks from the entire set of tasks. Then again, going forward, from block 1, you are doing a data sampling. You are not considering the entire data set, but you are considering only some part of the data. So that is what is called data sampling. So you are combining 2 methods of approximation here, task dropping and data sampling combined. So this is the overall execution of approximate Hadoop or approx Hadoop. So the paper is available in our tutorial paper bibliography. You can go through this paper, approx Hadoop. It's a very good framework that has been implemented on top of cloud infrastructure. Similarly, we have the Inc.approx. So this is another variation of Hadoop framework built especially on top of the Spark framework. Okay, so the previous one was approx Hadoop. This one is Inc.approx. That is incremental approximation framework. So here 2 different approximation methods are used: memoization and sampling. So what it does is that whenever the program, any kind of program is distributed into various parts and executed, it keeps some of the results of the previous execution of the program and removes some of the results on the basis of which results can be required in future. So they have a prediction model that predicts that this part of the result or this part of the entire execution of the program can be reused in future. Okay, so they store those parts of the program and results for future execution and remove those parts which are not required. So that is why the name memoization or memorization. Okay, so it memorizes the generated data and the parts of the program which generates the data for the future execution of the program. And sampling is similar to the method that has been used here. So not entire data set is used, but some amount of data that represents the entire data set. So we have to find some part of the data that actually is enough to represent the entire data set, or the skewness or the uniformity of the data set, and those part can be considered for further processing. So here similar method is used apart from memoization. So these 2 frameworks are present. The code for these 2 frameworks are present in GitHub. You can go through and you can download them and work if you are working with big data and machine learning tasks, and to speed up your process or to save some amount of energy compared to the exact execution of the Hadoop framework or the Spark framework, then you can use these 2 frameworks. So yeah, with this, I give the presentation pointer to Dr. Sunirmal Khatua to take forward. Thank you.
Thank you, Rishabh. Hello.
Yes, we can hear you.
Okay. And my slides are also visible, right?
Yes.
Okay. Thank you.
Yes.
So this is our last part of the presentation. So in the first part, Karthik and Rishabh, they discuss about the softwares that use the approximate computing, that by skipping some of the instructions, so we can reduce the overall energy. So in the last part of our tutorial talk, so we will discuss about at infrastructure level. So in the data center, they use lots of hosts, that how we can reduce the total energy consumed within the infrastructures. So combinedly, if you see, the goal of our tutorial talk is that we can approach from both the end. In the software levels, we can reduce the instructions, and at the same time, whatever the approximated set of instructions are going to be executed in the data centers, so the infrastructures can take reduced amount of energy to run those approximate instructions. So the key part that I will discuss here is the various power models that are used in the literatures to estimate what is the power consumed by those hosts or the data centers, and how can we predict the future powers consumed by the infrastructure and reduce the overall energy within the data center. And already Karthik has discussed that why it is so much necessary, and also predicted that by 2025, the data center will consume around 1/5 of the world's whole power. So it's huge. Now, if you see the pie charts there, that for data centers, the most of the power is consumed by the cooling devices. So it's around 50%. So that we do not have from the computer science perspective. But second dominating part, you can see that 26% is consumed by the servers and storage or the infrastructures. So that's why we are targeting that how we can reduce the overall energy consumed by the server and storage of the data centers. Now, in the lower one, in the lower pie chart, if you see that for individual hosts or individual servers, the majority part of the power consumed by the CPU utilizations. So how much CPU are execute the instructions. And the second one is the memory. And today with SSD and large amount of, for example, some terabyte scale of RAM itself in the today's hosts are there. So those RAM also, or the memory, in memory also takes a huge amount of power for that. So that's why we will consider individual servers. We will consider the servers of the data centers. We will consider mainly the CPU and the memory to reduce the overall infrastructure cost. Now, this is the overall organization of the data centers. I can skip this because we have only 20 minutes available. So in brief, we say that the hosts are basically packed in the racks with a rack-mounted switch. They are called the edge switch, and the edge switch are connected by aggregation switch, and which are connected by the core switch, and the core switch are basically connected to the outside internet. So whenever you put the task, if there is some interdependency among the tasks, so we have to try to place them as much as possible within the same rack, or we try to reduce the dependency of aggregation on the core switch. And within each of the hosts, they have some virtualization softwares involved that allow us to create some virtual machines to run your jobs. So ultimately, the virtual machine placement and the virtual machine migrations are the two key parts that has to be targeted to reduce the overall energy consumed by the corresponding hosts. Now, if you see that problem, so ultimately, since already we see that the CPU and the RAM are the two major parts of the power consumptions. So approximately they are more than 50% of the overall energy. So we can represent each of the physical machine as a big rectangle. So after normalizing the CPU and the RAM, we can represent them in the scale of 0 to 1, and they can be represented by the big rectangle. Now, whenever we want to run some tasks inside the virtual machines, the virtual machine also needs some small amount of the RAM and CPU. So in the same way of we can normalize the parameters, and we can represent the virtual machines also as a small rectangles. So now the problem center having a number of hosts. So we can say we have a set of big rectangles, and to that data centers, lots of requests come, and at the end, we need some virtual machine to meet those requirements. So we can have that. We have a huge number of small rectangles. We have a finite set of a small amount of big rectangles, and we need to place them, small rectangle into the big rectangle. So ultimately, it becomes a problem of packing those small rectangles into the big rectangle. So if we see how we can optimally pack it, so we need two decision variables. So the first decision variable X determines whether a particular virtual machine is placed in a particular physical machine. So Xik represents that the ith virtual machine is placed in a kth physical machine. And the second decision variable decide whether a particular physical machine is used or not. That means at least one virtual machine is placed in that physical machine or not. So our target is that if we can reduce the total number of running physical machine, then we can reduce the cost, so that those who are not utilized, they can be turned off, or we can move it to the sleep mode. So our objective is to minimize the total utilized physical machines. So the sum of the UK variables has to be minimized, so that it satisfies the resource constraints, specifically the memory constraints and the CPU constraints, and there is some constraints on the decision variables. So now if we can solve it, we can find what is the minimum number of physical machines needed to run all the jobs, and those who are not needed, they can be turned off or moved to the sleep mode. But we know that this solution is an NP-hard problem, NP-hard. So in real life, this total number of virtual machine requirements is huge. And for a data center also, these physical machines are also huge. So it's not possible to solve on the runtime to decide where to place it. So ultimately, we need some heuristics to solve a bin packing problem. So this is basically a 2-dimension 0-1 bin packing problem. And if we consider the other dimensions like the network, disk, or the cache misses, so all those things can be considered as a multi-dimension bin packing problem. And already we know that there are lots of heuristics for the bin packing problem. So instead of finding the exact solution to that, so these are also some approximate solution to this problem. So already we know that the first fit, best fit, and the worst fit are the 3 most popular heuristics to solve the bin packing problems. So in the literature also, they have used those variations slightly modified to get it. So for example, for energy perspective, this best fit decreasing is slightly modified to place the virtual machine in the hosts. So you can see that in that algorithm, so if you see there is an estimate power. So whenever we want to place some virtual machine in a host, so we estimate the power consumed. And we will choose the host for which this estimated power is the minimum. So now for this estimating the power, we need the proper power model, because without running it, we need to estimate it. So the power model is needed only for this part. And then we can estimate, and we have to place the virtual machines in the physical machines for which it is best fit. Here the fitness is determined by the estimated power consumptions if we place that virtual machine in the hosts. So we will discuss about the various power models that may be used to estimate the power without running it. So beforehand, or from the past history of the data, we can decide how much power may be consumed by that virtual machines. So for finding that various power models, so ultimately there are 2 approaches. One is called the software-based approach, and the other is a hardware-based approach. So ultimately, suppose this is the server under test, and there are multiple workloads are assigned to run it. So now we can get some parameters or metrics, for example, RAM utilization, CPU utilization by some softwares. That is the operating system. Mainly the operating system give a lots of performance counter. So we can get those data, or for some dedicated or specific kind of things, we can have some device that can be attached to the server called the power meters. So they can measure some specific requirement for that model, which are not provided by the web. So we add some hardware and get the performance data to a pre-processing module. Now that pre-processing basically convert those measured data to the normalized forms so that it can be used by a model that can be used by that model builder that will find some good power model to estimate what may be the power consumed by that server. And finally, they are basically evaluated which power model is best suited for a particular server and which is not. In general, those power models, whatever available in the literature, can be classified into 2 parts. So some consider the linear models and some consider non-linear models. Now for the linear models, again we see that if we assume that the slope and the intercept are not changed so much, so that is, if we have a fixed slope and intercept, then we can directly apply some mathematical formulas to predict what may be the to estimate what may be the power. So that can be applied for both linear as well as non-linear, provided we have a fixed slope and intercept. But if the slope and the intercept of that model varies with different data, so we cannot apply directly these mathematical formulas. So we have to apply some machine learning modules. And basically, most of that works, they consider some single variable linear regression, multivariable linear regression, and lasso regressions for that linear case, and some polynomial regression and some neural network based approach for non-linear case. So let me discuss about some of them, how those power models are used. So the first one, we consider that if we have a fixed slope and intercept, then how can we model that power estimations? So for a linear power models, we basically consider two parameters for that hosts. One is called the p mean, that is the ideal power. That is, we turn on that host and no workload is given. Then the power consumed is measured, and that is called the p minimum. So given any server, we can easily measure the value of the p min. Similarly, the p max means when the CPU utilization goes to 100%, that is the maximum power that consumed by that host. So again, we can give the highest workload so that the CPU utilization reach to the 100%, and we measure the power. So that Pmin and the Pmax can be calculated for any of the hosts given by simple tools. Even the operating system can also give some kind of power data. Now, this model says that the slope is the difference between the maximum and the minimum. The Pmax minus Pmin is the slope, and the intersect is Pmin. And that justified, because if you see the utilization 0, so if you put the value of the U equal to 0, the power is Pmin. And if you put the utilization equal to 1, this value comes to be the Pmax. So obviously, since this is linear, so for a particular value of the utilization of the CPU, we can easily predict what may be the power without actually giving that load and measuring it. So by that model, for any utilization, we can measure the corresponding power. Later, it has been found that the minimum Pmin, that is the minimum power or the ideal power for most of the hosts, are basically a fraction of the maximum power. So that fraction are identified by the variable k. So the Pmin can be replaced with the k times Pmax. So k is less than 1. So if you replace this, now this equation can be simply identified by that the slope will be 1 minus k times Pmax, and the intercept will be k times Pmax. So we do not need the Pmin anymore. So with only the measuring the Pmax and how much fraction it consumed, so we can also have a linear model on that. And in one of the work, they also shows that most of the server, so the value of the k is 70%. So if we replace that value of the k by 0.7, so we can find a very simplified linear power model, which mainly calibrated based on that Pmax only. So we will calibrate that Pmax, or we will measure the Pmax, and then for a particular value of the utilization, we can directly predict or estimate what may be the power consumed due to that utilization given in that host. So obviously the Pmax varies from host to host. But given that host, we know the Pmax, then we can estimate that if we give this much of the CPU loads, how much power may be consumed by that host. So that can be predicted. Now there is a work that also provides some nonlinear approach. So in this work, they consider the same slope, that Pmax minus Pmin, and the same intercept, but the variable is not linear with the utilizations. So in that work, they told that it can be 2 times utilization minus utilization to the power r. Here r has to be calibrated on that server. From the past data, we can predict it what is the value of the r, which is further simplified by double parameters. So instead of single parameter calibration, we can calibrate 2 parameters, alpha and beta. So alpha times utilization to the power beta. So from one host to the other host, so we can calibrate the values of alpha beta by measuring lots of values for different utilization, different power. We can calibrate the value of the alpha and beta, and we can predict utilization. So the advantage of the nonlinear is that if the exact power consumption in the host is not following the linear model, so this nonlinear model will give much more accurate data, accurate result than the linear model. Now, there is a software called the CloudSim. CloudSim is a popular one to simulate any cloud-related work, and that is also cited by lots of papers. So they use a power model called piecewise linear interpolation. So what they told that it can be a variable slope and variable intercept, but they assume that for a small interval, this is linear. So that's why it is called the piecewise linear interpolation. So we can measure for a particular piece, that is starting from P1 and the second one is P2. So if we can measure that at utilization of U1, UCPU1, the power is P1, and at the utilization of UCPU2, the power is P2, then we can find what is the power that comes for a utilization that comes within that interval. So here we can say that it's piecewise linear. So it can be that for the next slope, for the next values, it may not be in the same direction. So sometimes it provides much accurate result by having by reducing the gap between the two pitch or the size of the pitch. Now from this model, basically we get the power due to a utilization, but the utilization varies over time. So ultimately we need how much energy is consumed due to that jobs. So if you run a jobs, so that has a variable utilization of the CPUs or the various parameters. So then we need to integrate all the values of the this power model, power values that are estimated. But how can we integrate it? Because it's infinite. So for that, generally what we does is that we can convert this continuous function to a discrete functions with the duration of the gap as 1. So we can measure lots of these power values and we can just make a sum. So from that continuous space, it can be converted to a discrete space and we can measure estimation of the total energy consumed. And we can convert this power, the variable powers, to a particular energy for a duration of time. Now, for that machine learning based models, that is where the slope and the intercept are not fixed. So we can go for some machine learning models. So for the single variable linear regression, it's very simple. If we consider the single variable to be utilization of the CPU, then we can have that the regression function as the p equal to the alpha plus beta u. So that alpha and beta has to be calibrated replaced with the p mean, and we can just beta. So this beta is the slope. The slope is not constant. It's variable. So we have to calibrate for what value of the beta it can most accurately approximate the power. So that can give much better result instead of using that p max minus p min. If we calibrate this value of the beta for that host, and for a past data we can calibrate this value of the beta. Now, for if this is a multiple variable, so we can use more variables like CPU, disk, RAM, lots of things. So it can be in number of such parameters, and we can use a multivariable linear regression kind of things. And we need to find a solution of that parameter. So betas are the parameters of that model. So we can find this that minimize the mean square error. So this is the error or the noise induced. So we will find which minimize the square root of those error terms. And lasso regression, what it does, so basically if some of the parameters are not independent, then these regressions may not provide a better result. So what it does, it try to use the lasso regression by introducing some penalty terms. So this penalty term, what it does, it try to set some of the beta values to 0, which are not independent. So obviously some others are already taken care of, or so it will be taken as 0. So then we can reduce the total number of parameters. Instead of considering all those facts of the that host, we can consider only the parameters that are needed for that host. So lasso regression basically a multivariable linear regression, so with the penalty term introduced, that try to reduce the total size of the parameter space. Now there is a work that considers some neural network based solutions. So what it does is that from the host that measure the multiple parameters in different points of times.
So Sunirmal, if I can just interfere, there's just about like couple of minutes left. If you could see that you could adjust the times somehow. You could go like 5 minutes extra, but
Yeah, that's
if you
okay.
could
I can
check
finish
on that.
it.
Yeah, thank you.
Within 2-3 minutes, I will finish it. Okay, so we can consider a time window. So we measure the parameters continuously from the hosts, and then what it does is that within the window size of k, this considered as the input layer of that model. So this is a simple neural network model. Then they use the activation function as a ReLU because this ReLU provide this converge much faster than the normal activation functions like 10H or others. So that's why this activation function, these activation functions are taken from the past data. So whenever we train during the training phase, we can feed all the data and the power. So from there we can find the weight of those inputs and the weight of the bias. So we have an input vector and the bias vector, and that can be trained it for getting an output. So we get the output by that activation function of the ReLU. And then for the final output of the power, we use a simple linear functions of those output from multiple ReLU outputs. So there we don't use activation functions. It's simple the weighted average kind of things to get this output 2 is the final output of that. And in another works, so what they use a recurrent neural network kind of things. So it's called a Elman neural network, which is nothing but it's a folding of multiple states. So not only the simple user input, so that also memorize the previous states. So they store the previous one in the states. So in each times, the hidden layer take the input from the user as well as from the previous states, and then they activate it. And they use the same functions. So only difference is that we have a weight of the users. So that is represented by U matrix, and we have a weight of the states. So this is the W, and the bias factor B1. And then again they use the activation function. This activation function can be this ReLU or TANH or any activation function or simple sigmoid function. And based on that, again the final layer is a linear one, so to predict it. So that way we can predict some power in the future. And also there is a simple techniques that instead of going to so much complex things, if it follows a time series data, so we can use a Markov chain based prediction also. In Markov chain based prediction, what it does, that measure the previous power or the previous utilization kind of things, and then they convert it to a transition probability matrix from that past history data, and then we can find the transition matrix. Now from the transition matrix, we will see that the last state was S3. So that's why we'll go to the third row and find which state has the highest probability. So since the first state has the highest probability, so we will predict that the next value will be H1. Now for the others, we can use that Markov chain equations to get what may be the next row for the next prediction level. So we will calculate the next pi, and for which it is maximum, we will predict the values accordingly. So that way, based on that Markov chain based prediction also, we can provide what may be the power in future if we have a time series data of the previous power models. So ultimately the utilization has some impact on the power, and utilization, if the utilization follows some time series data, so obviously based on that Markov chain based prediction, we can predict the future power. And I can skip this part as well because this is not so much important. So we also have in our lab, we have 6 nodes. So right now in that figure, it's an old figure. There was a 3 nodes VMware. So right now we have 6 node VMware having that Intel Xeon Gold with 128 cores and 1 TB of physical memory and 20 terabytes of disk space. So this kind of environment we have in our labs, and we measure it. So if anyone is interested to collaborate, so we are happy to collaborate with them. So this much from my side. So hand over to you.
Thanks, Sunirmal. I just want to check from the participants if there's any questions for the team, and if so, if you could just either raise your hands or if you could just post it in the Q&A, I can moderate that. So while these questions, if there's getting posted, I just wanted to check. I mean, in case if you have any of your work in the form of a readily available library or some form of a bundled code which people can use, you may want to please share that. That might be useful for people who wanted to look out for ready pieces of part codes, or for either approximate computing or for these measurement or measurement of the powers.
Rishabh already told that in the GitHub he has put some.
Yeah. So
Yeah,
okay. Yeah. So if you could just post it as part of your in the message or in this thing, so it would be part of this, and therefore
sure,
people
sure,
can see it. Yeah.
sure. I'm posting it.
Okay. Looks like there's no questions. So I would request the speakers to just switch on their cameras. We'll just have one photo session, and then I think we can conclude the session. If you could please switch on your cameras and give. Let's do the cheese moment, and thank you so much. Okay, I have taken a clipping of the session, and thank you so much. I think it was a wonderful session. There was a lot of details. I think once your slides are available, all the participants can have a look at that. And I hope if there's any queries, they can reach back to you and use portions of your work in their work. Okay, thank you so
Sure.
much,
Thank you.
and looking
Thank
forward
you.
to meeting you in the other tutorials.
Thank
Thank
you.
you. Thank you very much.
Bye, everyone.
Bye.